We rely on computer security research to protect global digital infrastructure, but the research itself suffers from a structural deficit in scientific reliability. A review of published malware research identified significant gaps in methodology. 25% of papers rely on questionable dataset assumptions, and 71% omit basic safety precautions entirely. To determine if these failures represent an industry-wide trend, a longitudinal study evaluated nearly 750 machine learning security papers published over a 10-year span. By examining a decade of research, the team sought to quantify how many of these high-level claims could actually be verified through independent testing. This measurement study focused on the most prestigious venues in the field, beginning with the USENS Security Symposium. It also included the Network and Distributed System Security Symposium, or NDSS. The third major pillar analyzed was the ACM SIG-SAC Conference on Computer and Communication Security. Finally, the researchers reviewed a decade of publications from the IEEE Symposium on Security and Privacy. Because these are Tier 1 conferences, they represent the absolute highest standard of peer review. Yet, as the study reveals, even these premier venues have become vulnerable to non-reproducible research. The study split its evaluation into two phases. Indirect reproducibility checks if the necessary artifacts are even available. Direct reproducibility tests if the provided code actually runs. To even attempt the first phase, authors must provide three components: method, data, and experiment. The method requires a complete description of the analytical process. In machine learning, this involves documenting the exact hyperparameters used to train and calibrate the models. The data pillar relies on accessible datasets. The paper needs to provide explicit sourcing to open access databases so that future researchers can use the same inputs. Finally, the experiment phase requires the release of the actual execution scripts and source code used to generate the paper's results. The study found that while many papers claim transparency, a significant percentage fail to provide all three of these pillars simultaneously. Without these components, a GitHub link in an appendix is often just a hollow gesture rather than a tool for scientific verification. When researchers attempted to actually run the code during the direct reproducibility phase, they encountered a series of technical hurdles. It starts with the README file, which serves as the instruction manual for the entire experiment. This chart shows the state of experimental documentation. Only 57% of the evaluated repositories contained a README with functional setup instructions, leaving a 43% gap in basic guidance. Even when authors share raw data, many omit the preprocessing scripts or labels. This creates a dead-end wall for outside researchers who cannot format the data to match the original experiment. The study also found a recurring problem with missing pre-trained models. Many researchers base their results on external models, but fail to include the actual model files in their repository. In some cases, authors provided the functions and data, but expected the end user to write the actual execution scripts themselves to recreate the results. A project only becomes reproducible when every file, script, and model required to recreate the pipeline from scratch is meticulously provided. To address these gaps, Tier 1 conferences began integrating artifact evaluation committees, or AECs, around 2020 to review code and data before publication. The study used this 2020 milestone to test a null hypothesis. Did the presence of these committees actually increase the amount of available code? This graph shows the baseline availability of artifacts remained stagnant. There's no significant increase in authors sharing code after AECs were introduced. However, the quality of shared code improved. Artifacts passing through the AEC process execute at a significantly higher rate. To close the reproducibility gap, the study recommends that researchers design for verification from the start, utilizing self-contained environments like Docker instances or virtual machines. While institutional review helps, the responsibility for providing a complete, functional artifact still rests with the individual researchers. Verifying modern computer security research requires a complete package: exact datasets, full preprocessing pipelines, and isolated execution environments. This level of transparency converts a research claim into a verifiable discovery, allowing the community to build on a foundation of proven data. In computer security, a result that cannot be replicated is simply a claim that hasn't been proven yet.